Hi everybody. I had a student ask me about work session 17 question 4, and I'm really glad the student asked this question in particular. I find that it might be the most trickiest in this particular work session. So I want to kind of talk about it conceptually with you so you can begin to visualize what's going on in this question as if you're in the laboratory preparing this buffer and adding HCl to it to break the buffering capacity. So let's read the question together. It states that you have a 100 milliliter buffer solution and it has 0.1 molar in ammonia and 0.125 molar in ammonium bromide. What mass in grams of hydrochloric acid does this buffer neutralize before the pH falls below 9.0? Okay. So let's just write down some things that we know. Okay, what's in my beaker? We're working with a buffer. And anytime you recognize that you have a buffer in your beaker, I recommend that you write down the Henderson-Hasselbalch equation because you're definitely going to use it at some point. And so the Henderson-Hasselbalch is pH is equal to the pKa plus the log, and we've learned it to be the conjugate base represented generically as A minus over its weak acid or conjugate acid, HA. Alright, so that's just something to be aware of. We also recognize that we have a 0.100 molar ammonia solution. So I like to write down, like, what is ammonia? NH3. Okay, awesome. What is ammonia? NH3? It is a weak base. Good. So just recognizing that that's the weak base component. And then we also have a 0.125 molar. This is ammonium bromide. Now remember when we purchase chemicals, and let's say we want an ion, like ammonium, NH4+. Well, you can't just purchase NH4+. You purchase it as the salt, right? So it needs to be partnered up with a counter ion, for example. In this case, it was bromide, Br minus. You could use chloride. So back in Chem 1A, or first semester Journal of Chemistry, when you dissociate ammonium bromide, remember all ammonium salts are soluble in water, you would get ammonium plus bromide. Bromide, if you were doing like some sort of precipitation reaction, would have been the spectator ion. And in this case, for us, it would be the spectator. Just nothing, it's not going to change the pH of our solution or have any sort of impact in terms of the buffering system, right? Because we understand that a buffer is composed of what? The weak base and its conjugate acid, or weak acid and its conjugate base. They have to be pairs, though. They have to be partners. So something to recognize here is that this is the weak acid. So when we write the equation, I generally like to write the more simplified form, like where's the chemistry happening? And I don't always include those counter ions like bromide or chloride if they're just not playing a role in the whole reaction, right? In this case here. So, okay, so we have a weak base, weak acid, and we will be adding HCl. HCl is a what? It's a strong acid, right? And when we put HCl in solution, it dissolves into protons and then the chloride anion. Once again, these chloride anions are just going to be spectators, not really participating in the buffering system, not going to affect the pH. And so when I think of HCl or a strong acid, I think of it donating protons in solution, and we understand now that protons don't exist just as protons, but rather as hydronium ions. So I'm just trying to lay out the foundation of what is happening here in your beaker. What are the key players in this buffering system, right? We recognize from Henderson-Hasselbalch. Now we can apply Henderson-Hasselbalch to this actual buffering system, and we recognize that we need the weak base on top, ammonia, over the weak acid, right? And so it's important that not only do you use the Henderson-Hasselbalch, but you know how to use it and apply it to differing buffering systems. So this is an ammonia-ammonium buffer. All right, so when we work with Henderson-Hasselbalch, we always work with the pKa, right? And when you're looking at Kas or Kbs, you're probably going to find the Kb of ammonia. That's very common in the back of your textbook in the literature constant table. And the Kb is 1.76 times 10 to the negative fifth. Now you can calculate Ka from there, or you can calculate pKb. There's different ways to get to the pKa. So the way I did it was I took the pKb, which is the negative log of the Kb, and that is equal to 4.75448. Remember that when you take the p of anything, it's always the negative log of that. So pH is the negative log of the proton concentration or the hydronium ion concentration in solution. Now if you want to find pKa from pKb, you just have to subtract it from 14. And so the pKa would be of ammonium, in this case, 9.2455. So if I prepared a buffer that was equal concentrations, equal amount of ammonia to ammonium, the log of 1 is 0, then the pH is equal to the pKa. But in this question here, we're asked how much HCl can I add to have the pH before the pH falls below 9. So really the question is asking, well, how much HCl can I add to get the pH to 9? Okay, and then anything more than that will have it fall below 9. So here we'll put 9.0 for the pH for the Henderson-Hasselbalch is equal to 9.2455 plus the log of ammonia over ammonium. So the cool thing about the Henderson-Hasselbalch is it allows you to calculate the new ratio of the base to the acid, right? Like I said before, if it were equal, then this ratio would be 1. Log of 1 is 0. So therefore, pH is equal to pKa. So pH would be 9.2455. However, I want the pH to be 9. And the only way I can do that is by adding a strong acid. And that will therefore change the ratio of ammonia to ammonium. And when you're in the laboratory, let's say you're doing some research in a biochemistry lab, you're going to be preparing a lot of buffers. You're going to be doing this sort of chemistry where you're making your buffer solution. You need to figure out, well, what's the correct ratio of the base to the acid using the Henderson-Hasselbalch equation, right? And so, in this case here, when you solve for the ratio of ammonia to ammonium, you would get 0.568198, right? So that's what the ratio is going to be. It's not, 50-50 here, right? All right, so, and to get to that ratio, we'll be adding HCl, and this is where we will be using the BA table. Remember when I taught you in the lectures, we use the BA table to do solution stoichiometry when everything is 1 to 1 to 1. So instead of doing dimensional analysis like you would have learned in first semester general chemistry, we're going to be doing the BA table to simplify. So you're actually running a reaction. This is not equilibria where you would use a rice table. I know that can be a little confusing at two different tables. Rice for equilibria, BA table for when you add something like a strong acid or a strong base and you're running a reaction. And that is, just solution stoichiometry. So we're adding the hydronium, we're adding HCl, which is in the form of the hydronium ion. So hydronium ion comes from HCl. Which component of my buffer will it react with? Will it react with the ammonia or the ammonium? Good. Hopefully you said ammonia. Remember, acids want to react with bases. Two acids don't want to react together, right? So we would write ammonia And this reaction goes to completion because we'll have a limiting reactant, the hydronium ion or the HCl. And so everything here, 1 to 1, this is a proton, ammonia is a proton acceptor because it's a base. Hydronium ion is acidic, it's a proton donor. What is the conjugate acid of ammonia? Ammonium, good, because it accepted a proton. And the conjugate base of the hydronium ion would be what? Water, good, because it lost a proton. Fantastic. That's probably the hardest part here, is kind of recognizing what is happening when I add the HCl. Those hydronium ions, what do they react with? They react with ammonia. And so before the addition, before we add anything to our beaker, we have negligible amount of hydronium ion solution. Yeah, I know there's some in there due to slight ionization of water, but nothing to really make a significant impact. We do have a certain amount of ammonia and ammonium. And remember with the Ba table, we always need to work in moles, okay? So coming back to the actual problem itself, we had started off with the concentrations and the volume of solution. From there, we can figure out the number of moles. So you can take 0.100 moles of ammonia solution per liter of solution and multiply it by 0.100 liters. It was 100 milliliters, so I divide it by 1,000 to get 0.1. And you would find that you have 0.0100 moles of ammonia that you put into your beaker when you first made your buffer. So that's what I'm going to put. B stands for before addition. Same thing for ammonium. So we would put 0.0125 moles of ammonium into our beaker when we're first preparing our buffer. Now we're going to be adding HCl. We don't know how much we're going to add, but we add a certain amount. And so I'm just going to represent that by plus x. Right? I'm adding a certain amount. I want to solve for that x. That's my variable. When I'm adding the HCl, what is it reacting with? Ammonia. So you want to subtract x from that because it's going to react 1 to 1, so it's going to decrease the ammonia. But what is it going to do to the ammonium? We're going to create more of that. So this is a plus x. Now remember, we don't want to break the buffer. And the question says how much do we add so that it's still neutralizing all the HCl that's added. That means at the end, HCl or the hydronium ion is our limiting reactant, and we should be left with what after addition? Second letter A stands after addition. This should be 0 at the end. It should be completely neutralized, right? The buffering is still working at this point. But what we'll notice is that the original amount of ammonia is going to decrease because it's reacted, and the original amount of ammonium will increase because we've produced more ammonium in solution due to this reaction. Okay, so the ratios have changed. We already know what the ratio needs to be. Remember, we're trying to figure out how much are we adding of this. That x is right there, so we need to solve for x. We already know what the ratio should be of base to acid to get us to pH 9. So we're going to use that number right now. So 0.568198 is equal to, remember, base over acid. A lot of times students will get to this step and they'll accidentally invert them. So just be careful that you always ask yourself, okay, what does the ratio look like? Base over acid. And from here, we can solve for x. When you do the algebra, the x you should get here is 0.001847,678. I always like to keep a lot of digits just so I don't have any rounding error. Remember, this is x. X stands for the amount of moles of HCl or the hydronium ion added, right? And so this is moles of HCl essentially, or the hydronium ion. Remember, it's the same thing, 1 to 1. And we want to know how many grams we can add. Then we just need to multiply by the molar mass. And that is equal to 0.0674 grams of HCl. All right, so let's talk about this again, because I know we're getting kind of super theoretical here. I want to make sure that this theory can be visualized, right? So when I'm in the laboratory, I've made a buffer. I've added 0.01 moles of ammonia and 0.0125 moles of ammonium. Now I want, when I create my buffer, I want to make sure the pH falls to 9.0, right? I can figure out the ratio to get that of base to acid from the Henderson-Hasselbalch equation. Need to make sure I know the pKa of our buffer system to find that ratio, what that would look like. I needed to use the BA table in order to figure out how much of the HCl that was added to get to this ratio, right? And these were the initial amounts, and then this is how it would change, minus x plus x. And when I solve for x, that helped me to back calculate the number of moles of HCl that was added to reach my ratio here. Always remember that when you're looking at what's in your beaker, to really identify, is it a weak base, is it a weak acid, is it a strong acid that I'm adding? Try to visualize the process and how, what you're having in this case here, this buffer is changing when I add the acid. It's really important to recognize that the acid component will react with the base part of your buffer, and then you're going to be creating more of that conjugate acid in solution. And so that's where these, X's are changing. Now, please do not confuse this with the rice table. I know with the rice table, you automatically say minus x and plus x, and that is the change to reach dynamic equilibrium. Here, we're actually doing some stoichiometry here. We're doing a full reaction, and that's why the arrow is going straight forward there, right? And we understand that we're neutralizing all of our strong acids, so that's why we're left with zero amount in the end, because it's completely neutralized by the ammonia of our buffer, okay? If you have any questions, don't hesitate to reach out to me, and I hope that this provided some clarity for you all. And I look forward to chatting more about this. I would recommend trying to do this problem again without looking at the solution and explaining it in your own words. Perhaps drawing it out. Draw your beaker, pipette in your HCl, and try to think, okay, how is the pH changing? Why am I using the BA table here? How is this helping me solve for the amount of HCl added? If you can explain it in your own words, then you can confidently know that you're doing it correctly. Right, good luck, and we'll talk.